Hello everyone. Today we will going to see some practice questions from the chapter Physical and Chemical Equilibrium. So this is our part 6. Let's start. Disclaimer which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Index slide. So we will going to see some practice questions from question number 42 to question number 49. Let's start with question number 42. Formaldehyde polymerizes to form glucose according to the reaction. This 6-HCHO will giving us glucose C6H12O6. The theoretically computed equilibrium constant for this reaction is found to be 6 into 10 to the power 22. If 1 molar solution of glucose dissociates according to the above equilibrium, the concentration of formaldehyde in the solution will be. Options are 1.6 into 10 to the power minus 2 molar, 1.6 into 10 to the power minus 4 molar, 1.6 into 10 to the power minus 6 molar, or 1.6 into 10 to the power minus 8 molar. You have 10 seconds to solve this question. After that, we will see the answer. Okay, let's see. So we have our correct answer is option B, that is 1.6 into 10 to the power minus 4. So a very high value of K for the given equilibrium. You can see that the equilibrium constant for given reaction is 6 into 10 to the power 22, right? It is very high value for the K. So it shows that dissociation of glucose to form formaldehyde is very small. If we see that if the dissociation of glucose will happen to the formaldehyde, it will be very small, right? Because K for that reaction will be much smaller, right? So hence at equilibrium we can take that the C6H12O6 is 1 molar. We can take the concentration of C6H6 is 1 molar, and it is given also that 1 molar solution of glucose dissociates. So concentration of C6H12O6 we know that is 1 molar, and K can be written as C6H12O6 divided by the concentration of reactant, that is HCHO, to the power 6, because 6 is the stoichiometric coefficient of formaldehyde, and we have K value as 6 into 10 to the power 22 is equals to C6H12O6 will be 1 divided by HCHO to the whole power 6. And from this we can calculate the concentration of formaldehyde by this formula, 1 upon 6 into 10 to the power 22 to the whole power 1 by 6. We just interchange the terms in this equation, and the final concentration for formaldehyde is coming out as 1.6 into 10 to the power minus 4 molar. Okay, and thus our correct option B is the right answer. Okay, let's move to next question, question number 43. 1% CO2 in air is sufficient to prevent any loss in weight when M2CO3 is heated at 120 degrees Celsius. Now M2CO3 dissociating into M2 and CO2. M2CO3 is in solid form, M2 is in solid form, and CO2 is in gaseous form. The Kp for this is 0.0095 atmosphere at 120 degrees Celsius. How much would the partial pressure of CO2 have to be to promote this reaction at 120 degrees Celsius? So we have to find out the partial pressure of CO2. Options are: partial pressure of CO2 is less than 0.0095, partial pressure of CO2 is equals to 0.0095, partial pressure is greater than 0.0095, or cannot be predicted. So you have 10 seconds to solve this question. After that, we will see what will be the answer. Okay, so our correct answer is option A, that partial pressure of CO2 should be less than 0.0095. So we have given this reaction M2CO3 giving us M2 and CO2. Now, if we want to calculate the Kp for this reaction, that is equilibrium constant or pressure constant, it will be partial pressure of CO2 only, because only CO2 is in gaseous form. Rest of the product and the molecule, product and the reactant are in solid form, so their partial pressure will become 1. We take it as 1. So Kp will become equal to the product partial pressure, that is only for CO2. So partial pressure of CO2, and Kp we know given is 0.0095 atmosphere. Now, since CO2 is 1% in air, it is given. So partial pressure of CO2 will become 1 by 100 into partial pressure of air, right? So it is coming out as 0.01. So partial pressure of CO2 will become 0.01, right? And since you can see that 0.01 is greater than 0.0095, and if this is if 0.01, if we consider 0.01 as the partial pressure of CO2, then the reverse reaction will favor. But we have asked that the how which partial pressure of CO2 have to be promote this reaction at 120 degrees Celsius. So according to Le-Chatelier's principle, the partial pressure of CO2 should be less than 0.0095, as 0.0095 is Kp and is also equal to partial pressure of CO2. So to manage this reaction to in the forward direction, and to promote this reaction at 120 degrees Celsius, so according to Le-Chatelier's principle, the partial pressure of CO2 should be less than 0.0095. It should be in this range, and thus our correct answer is option A, that is partial pressure of CO2 is less than 0.0095. Okay, moving on to next question, question number 44. Starting with 1 mole of O2 and 2 moles of SO2, the equilibrium for the formation of SO3 was established at a certain temperature. If V is the volume of vessel and 2x is the moles of SO3 present, the equilibrium constant will be. So we have given initially 1 mole of O2 and 2 moles of SO2, and we have given that the volume of vessel is V and 2x is number of moles of SO3 present at equilibrium. So we have to find out the equilibrium constant. Options are x square V divided by 1 minus x whole cube, 4x square divided by 2 minus x into 1 minus x, 1 minus x whole cube divided by 2v, x square divided by 2 minus x into 1 minus x. So you have 10 seconds to solve this question. After that, we will see what will be the answer. Okay. So the correct answer is option A, x square v divided by 1 minus x to the power whole 3. So we have given this, we consider this reaction of formation of SO3, that is 2SO2 plus O2 will give you 2 molecules of SO3. Initially, it is given that 2 moles of SO2 is present and 1 mole of oxygen is present. And initially, SO3 will be of 0 moles. Now at equilibrium, SO2 will remain, the remain SO2 will be twice of 1 minus x, that is 2 minus 2x, and or for O2 it will be 1 minus x, for SO3 it will be 2x. Now if we find out the molar concentration, it will be the number of moles divided by the volume. So it will be 2 minus 2x divided by V, 1 minus x divided by V, and 2x divided by V for SO2, O2 and SO3 respectively. Now Kc is given by the product concentration divided by the reactant concentration. So product is SO3 and its concentration is 2x by V. So 2x by V to the power 2, because 2 is stoichiometric coefficient for SO3, divided by 2 minus 2x upon V to the power 2, because SO2 has 2 as stoichiometric coefficient. It will come into power and multiply by 1 minus x divided by which is the concentration for O2. Now, on solving this and dividing these two terms, we have Kc is equals to x square v divided by 1 minus x to the whole power 3. 1 minus x whole cube. And this is our correct answer, and thus our option A is the correct one. Let's move to question number 45. For N2 plus 3H2 giving us 2NH3, 1 mole of N2 and 3 moles of H2 are at 4 atmospheres. We have given initially that 1 mole of N2 and 3 moles of H2 are present at 4 atmosphere. Now equilibrium pressure is found to be 3 atmosphere. The pressure will decrease at equilibrium, and we have to find out the Kp, equilibrium or pressure constant. Options are 1 upon 0.5 into 0.15 whole cube, 1 upon 0.5 into 1.5 whole cube, 3 into 3 divided by 0.5 into 0.5 whole cube, or none of these. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, so let's see what will be the answer. So the correct answer is option B, 1 upon 0.5 into 1.5 to the power 3. So as you can see that this is the reaction given in the question, N2 plus 3H2 giving us 2 moles of NH3. Now initially it is given that N2 is 1 mole and H2 is 3 mole and NH3 will be 0. So at equilibrium N2 will be 1 minus x, H2 will be 3 minus 3x, and NH3 will be 2x. Now as we can see that initial moles, total moles are 3 plus 1, 4, and pressure initial is 4 atmosphere. Now at equilibrium, moles, that is N2, will become 1 minus x plus 3 minus 3x plus 2x, which is 4 minus 2x. And at equilibrium, it is given that pressure will become 3 atmosphere. So we just put it in the equation. So initially PV equals to nRT. So P initial is 4. So 4V equals to final moles or total moles initial is 4. So 4V is equals to 4RT, and this implies that V is equals to RT. Now at final, at equilibrium, PV equals to nRT and P will become 3. So 3V is equals to, and total number of moles is 4 minus 2x times RT. So we can put V equals to RT as we have find out here. So 3 times RT is equals to 4 minus 2x RT, and on solving this equation, we have 3 equals to 4 minus 2x. This implies that x is equals to 0.5. So we have x value 0.5. Now we can find out the mole fraction of nitrogen, which is the moles of nitrogen divided by total moles in the solution. So 1 minus x divided by 4 minus 2x, and on putting x, we have mole fraction of N2 is equals to 0.5 by 3. Similarly, mole fraction of H2 is 1.5 by 3, and mole fraction of NH3 is 1 by 3. Now, partial pressure of N2 will be 3 multiplied by 0.5 by 3. That means total pressure into the mole fraction, it will be 0.5 atmosphere. And similarly, for the H2 molecule, the partial pressure of H2 molecule will be 0.5 into 3, number of moles into mole fraction, and it is coming out as 1.5 atmosphere. And in the same way, we will find out the partial pressure for ammonia molecule, which is 1 by 3 mole fraction multiplied by total number of, 1 by 3 partial mole fraction multiplied by total pressure, which is 3. So partial pressure of NH3 is coming out as 1 atmosphere. And Kp, we have to find out Kp in the question. So Kp will become, according to the equation, the product pressure upon the reactant pressure. So partial pressure of ammonia to the whole power 2, because 2 is stoichiometric coefficient, and divided by the partial pressure of N2 multiplied by partial pressure of H2 cube. Now on putting the values, we have 1 upon 0.5 into 1.5 to the power 3, 1.5 cube. And this is the option given in our question. Hence, this is the correct answer. So our correct option will become B option, giving us the correct answer. Okay. So let's see next question, question number 46. Reaction between nitrogen and oxygen takes place as following. 2N2 plus O2 giving us 2N2. If a mixture of 0.482 mole of N2 and 0.933 mole of O2 is placed in a reaction vessel of volume 10 liter and allowed to form N2O at a temperature for which Kc is equals to 2.0 into 10 to the power minus 37, the equilibrium concentration of N2O will be. So we have to find out the equilibrium concentration of N2O. So options are 7.06 into 10 to the power minus 20 mole liter inverse, 6.58 into 10 to the power minus 21 mole liter inverse, 4.82 into 10 to the power minus 4 mole liter inverse, or 9.36 into 10 to the power minus 7 mole liter inverse. So you have 10 seconds to solve this question, and after that we will see that what will be the answer. Okay, so let's see. The correct answer is option B, 6.58 into 10 to the power minus 21 mole liter inverse. We have given this reaction in the question. 2N2 plus O2 will give you 2N2O. Initially 0.482 and 0.933 moles are present for N2 and O2. It is given in the question, right? And at equilibrium, the N2 moles will become 0.482 minus 2x. O2 moles will become 0.933 minus x, and N2O moles will become 2x. Active mass, if we find out, it will be 0.482 minus 2x divided by 10, that is volume, so it is concentration. So 0.933 minus x divided by 10 for O2 and 2x by 10 for N2. Now we have given the Kc for this reaction is 2 into 10 to the power minus 37, and we have to find out the equilibrium concentration of N2, that is 2x by 10. So let's see. The magnitude of Kc is very, very small, such that at equilibrium, the concentration of N2, that is 0.482 minus 2x divided by 10, will become equal to 0.482 divided by 10. So 2x will be, deleted, or uh, 2x will not be considered because the Kc value is very small. So it will be equal to 0.0482. So N2 concentration at equilibrium will become 0.0482 mole liter inverse. And similarly, in the same way, O2 concentration at equilibrium will become 0.0933 mole liter inverse. Now, Kc for the reaction is product concentration divided by reactant concentration. So N2O to the power 2 divided by N2 to the power 2 into O2. So Kc is given, we put the value, and N2O we have taken as a 2x by 10, so on square it become 4x square by 100, and N2 we have 0.0482 whole square, O2 0.0933. Now we just solve this equation and we just find the value of x, because x is the only variable in this equation. So x is equals to 3.29 into 10 to the power minus 20. Now we have to find out the N2O concentration, which is, we have taken 2x by 10, so we have to solve this. So it will be 2 multiplied by the x value and divide by 10. And the final concentration for N2O is coming out as 6.58 into 10 to the power minus 21 mole liter inverse, right? And hence we have our correct answer or correct option as option B, 6.58 into 10 to the power minus 21 mole liter inverse. Okay, let's see next question, question number 47. The values for Kp1 and Kp2 for the reactions first and second. First is X dissociating into Y and Z, Y plus Z, and A is giving us 2B, are in the ratio of 9:1. So basically we have the values of Kp1 and Kp2 for these two reactions as 9:1. If degree of dissociation of X and A be equal, then total pressure at equilibrium of reactions first and second are in the ratio. So we have to find out the total pressure at equilibrium of these reactions. or it will be in the ratio. So options are 3 is to 1, 1 is to 9, 36 is to 1, or 1 is to 1. You have 10 seconds to solve this question. After that, we will see what will be the answer. Okay, so let's see. So the correct answer is option C, that is 36 ratio 1. Now, let's suppose the total pressure at equilibrium for the reaction first and second are P1 and P2 respectively. Then, if we find out, if we looking at moles, so X is giving us Y plus Z. So initial moles, let's suppose X is 1 and Y is 0 and Z is 0. And at equilibrium, the moles of X will become 1 minus alpha, Y will become alpha, and Z will become alpha. So total moles will be 1 minus alpha plus alpha plus alpha, that is 1 plus alpha. If we find out the partial pressure for X, it is 1 minus alpha upon 1 plus alpha, basically mole fraction multiplied by the total pressure. Similarly for Py and similarly for partial pressure for Z. So these are the values for partial pressure of X, Y and Z, where P1 is the total pressure we have considering. Now what we will do, Kp1, if we calculate, it will be the partial pressures of product divided by partial pressure of reactant. So products are Y and Z, so alpha upon 1 plus alpha P1 to the power 2, because both for Y and Z the partial pressure are same, and divided by the partial pressure of X, that is 1 minus alpha upon 1 plus alpha into P1. On solving this, we have Kp1 is equals to alpha square P1 divided by 1 minus alpha square. Now we have given our second equation, which is A giving us 2B. Initially, A is 1 and B is 0. And at equilibrium, A is 1 minus alpha and B is 2 alpha. Total moles will become 1 minus alpha plus 2 alpha, 1 plus alpha. Now the partial pressure of A will become 1 minus alpha upon 1 plus alpha into the total pressure. And partial pressure of B will become 2 alpha upon 1 plus alpha into P2. So Kp2, if we count, it will be the partial pressure of products divided by partial pressure of reactants, and it is coming out as 4 alpha square divided by 1 minus alpha square P2. Now we have to find out the ratio of Kp1 and Kp2 for these two reactions given in the question. So we divide Kp1 and Kp2. So Kp1 divided by Kp2 will be alpha square P1 divided by 4 alpha square P2. On cancelling out alpha, and we have P1 divided by 4 P2, that is equals to 9 by 1, which is given in the question also, right? That Kp1 and Kp2 ratio is 9 ratio 1. Now P1 by P2 ratio will be 36 divided by 1, because if we solve this equation, we have 4 comes here in the right hand side. So P1 by P2 will become 9 into 4, that is 36 divided by 1. So P1 divided by P2 will become 36 ratio 1, right? So our final answer will be 36 divided by 1. And as we have asked that P1 ratio P2 we have to find out, so it will be 36 ratio 1, and hence our C option is the correct one, that is 36 ratio 1. Okay, let's see the next question. Question number 48. The following equilibrium constants are given. N2 plus 3H2 giving us 2NH3, the equilibrium constant is K1. N2 plus O2 giving us 2NO, equilibrium constant is K2. And H2 plus half of O2 giving us H2O, equilibrium constant K3. The equilibrium constant for the oxidation of NH3 by oxygen to give NO is. Now we have a reaction here, that we have given three reactions, and we will find that what will be the equilibrium constant for the oxidation of NH3 by oxygen to give us NO. So we have to write the equation or reaction first. So options are K2 into K3 whole cube divided by K1, K2 K3 square divided by K1, K2 square K3 whole 6 divided by K1 square, K1 K2 divided by K3. You have 10 seconds to solve this question. After that, we will see what will be the answer. Okay, let's see. So the correct answer is option C, that is K2 square, K3 whole power 6 divided by K1 square. So we have asked the equilibrium constant for this equation. So our required equation for the oxidation of ammonia by oxygen to give NO is 4NH3 plus 5O2 oxidized in the presence of uh, platinum gauze 800 degrees Celsius temperature, giving us 4NO and 6H2. And for if we look in this reaction, we have K is equals to NO whole power 4 H2O power 6 divided by NH3 power 4 and O2 power 5, right? So we have to find out this through K1, K2 and K3. So if we write the K for the equation first, it will be NH3 whole square divided by N2 and H2 whole cube. It will be K1. And for equation 2, K2 will be NO whole square divided by N2O2. For equation third, K3 is equals to H2O divided by H2O2 to the power half. Now what we will do, for getting the K, we have to find out the K, right? So for K, we must, visualize, we just see and observe that we required K1 square, K2 square in K3 to the power 6. So we do it. So K1 square will become NH3 power 4 divided by N2 power 2 into H2 power 6. K2 square will become NO power 4 divided by N2 power 2 O2 power 2. And K3 whole 6 will become H2O whole 6 divided by H2 to the power 6 and O2 to the power 6 by 2, which is 3, right? And so we just observe and see that K in terms of K1, K2 and K3 is coming out as K2 square into K3 whole 6 divided by K1 square, and we have calculated these values for K1, K2 and K3. And now on substituting the values, we get that K is equals to NO whole power 4 H2O power 6 divided by NH3 power 4 and O2 power 5. And this is what we have to find out, right? And thus our correct option will become C, that the K will be equal to K2 square K3 whole 6 divided by K1 square. Okay. Let's move to next question. Question number 49. At 600 degrees Celsius, Kp for the following reaction is 1 atmosphere. X is giving us Y plus Z. At equilibrium, 50% of X is dissociated. The total pressure of equilibrium system is P atmosphere. What is the partial pressure in atmosphere of X at equilibrium? So we have to find out the partial pressure of X at equilibrium. Options are 1, 4, 2 or 0.5. So you have 10 seconds to solve this question. After that, we will see what will be the answer. Okay, let's see. So it is option A. So correct answer is option A. Let's see how. And we have given this reaction in the question. X is giving us Y and Z, and product and the reactant both are in gaseous form. So initially, if X is 1 mole, Y is 0 and Z is 0. So at equilibrium, it is dissociating 50%. So 1 will become 0.5, Y will become 0.5 and Z will become 0.5. And if we calculate total pressure, it will be 0.5 plus 0.5 plus 0.5, which is 1.5. And therefore, the partial pressure for X is the mole fraction into total pressure, that is 0.5 upon 1.5 into P. The partial pressure for Y will become 0.5 upon 1.5 into P, and partial pressure for Z will become 0.5 divided by 1.5 into P. So if we find out Kp in terms of partial pressure, so it will be partial pressure of Y product and into partial pressure of Z divided by partial pressure of reactant, that is partial pressure for X. Put the values in this equation. We have 1 because Kp is 1 is equals to Py. Py is P by 3 into Pz. Pz is also P by 3 divided by Px. Px is also P by 3. Now we solve this and we have P value as 3 atmosphere. So partial pressure of X will become P by 3 is equals to 1 atmosphere because we have taken here the partial pressure of X is P by 3 and we have calculated P value, that is 3 atmosphere. So 3 by 3 will become 1 atmosphere and hence the partial pressure of X will be equal to 1 atmosphere. And thus we have our correct option as A, that is 1. Okay. Okay, thank you.